Hey everybody, it's Mr. N here, and this is the next lesson. We're going to talk about rates of change and how we're going to apply them in something called rectilinear motion. So, let's first recall that when we have a rate of change, it's delta y over delta x, so f of x2 minus f of x1 over x2 minus x1. This gives us an average rate of change. For an instantaneous, we're going to take that slope at a particular point, so that's the limit as delta x goes to 0 of delta y over delta t. And that'll give us this tangent line because we're putting point P in Q, so we're moving point Q closer to P, and it'll give us the tangent line at point P, and on this graph it'll look like this, right? Just an approximation as we move point Q closer. So we know that the derivative is the slope, which is the instantaneous rate of change. And then we talked about these. For position, we will typically use s of t. A lot of times you'll also see it as x of t. And then if we take that derivative, we get the velocity. And we take the derivative of velocity, which is the second derivative of position, that'll give us acceleration. Third derivative of position, second derivative of velocity, first derivative of acceleration gives us something called a jerk function. They typically won't ask you anything about this. If you want to call it the Mr. N function, you can, but oh, come on, guys, I'm not. But in any case, so that's the jerk function. And the jerk is that initial push, that initial jerk, so to speak, to get something moving. We're going to apply this right now. This is a typical AP question where they would ask you a bunch of these, maybe not every single one of them, but a bunch of these types of things. So let's go ahead and practice this question. I need a lot of room for this, so let me move this all the way up here, and we will go over this. And on the first part right here, it says find v of t. So we're given s of t. So for part A, let's move this out of the way. So for part A, you got to excuse me, my Apple Pencil stopped working, so I'm using a stylus right now, so my handwriting might be not so good. So let's see how it works out. Okay, so right here for part A, it says find v of t. So v of t right here, let me change that size. That's a big ol'. V of t is going to equal, okay, now we're going to take the derivative, right? So it's going to be s prime of t right here. So this will end up being 3t squared minus 24t, 3t squared, minus 24t plus the 36. And remember, this is going to be our ds dt. Okay, so then for part B, we need to find the velocity. For part B, we need to find the velocity after 2 seconds, and then the velocity after 5 seconds. So I'm going to find v of 2. So v of 2 ends up being, I plug in 2 to my equation right here. So I'll plug in 2, so 2 squared, 4 times 3, minus 24 times 2, plus 36, and I will get a value of 0. So this comes out to be 0. My pen, again, I'm having issues, does not want to write, so this value is 0. Okay. So then, and this is in meters per second. Well, actually, yes, we're going to assume that it's meters per second. They did not give us the position, and it should be in meters, but we'll just go ahead and say meters per second. Okay, so then v of 5 is what's next, so I do the same thing. I plug in the 5, and I'm going to get negative 9 meters per second. Okay, for part C, this time, when is it at rest? Well, we know it's at rest when our velocity, right, is equal to 0. Well, we just did that. We found out that right up here, we found out the velocity is equal to 0 at 2. So one of our answers should be 2, but let's just set up our equation. 0 equals 3t squared minus 24t plus your 36. and you can factor this. And this factors into, we'll take a 3 out, and we're going to be left with t minus 6 and t minus 2. So this occurs at t equals 2 and t equals 6. And those are both seconds. Okay, so this is when my velocity, when the particle will be at rest when the velocity is equal to 0. Okay, so for part D over here. So on part D, we need, it says, when is it moving forward? So we need to be moving in that direction. All right, well, how do we find out when something is moving forward? Well, it's moving forward when the velocity is positive, so I need v of t to be greater than 0. So this is moving forward. Okay, backward would be v of t less than 0. At rest, v of t is 0. So we need to know when v of t is greater than 0. Well, I already did v of t, and I factored this out in the problem before to be 3 times t minus 6 right here, and then t minus 2, and then I need this to be greater than 0. Well, how do we do this? Well, you learned how to do these in previous courses. One way I would recommend is to use a number line, and you have your two values right here at 2 and at 6, and you need to test the intervals to see where the velocity, where the equation is positive. That's going to give me a positive value. So, in other words, if I test a value less than 2, 0, I will get positives right here. If I test a value between 2 and 6, pick 4, plug it into the equation. Okay, and where am I plugging it? I'm plugging it into v of t. Right, I'm plugging it into my v of t equation that I solved for right here. Let's highlight that because we're using that a lot. It's our s prime of t, which is really our v of t. Okay, so that's what I'm using, and I'm plugging in 4. Well, I'll get negatives right here. And I plug in 7. I'll get positives, so I plugged in a number greater. So that means there are two regions where it is greater than 0, right in here and right in there. So let's express what those regions would be. And those regions would be the velocity is greater than 0 when t is less than 2 and t is greater than 6. So those are the points where my velocity is greater than 0, and thus I will be moving forward. So this is forward. If I wanted backwards, then I would need to know when the velocity is less than 0. All right, let's slide this up again because I told you we're going to need a lot of room in this. So we did part D. Now let's look at part E. And part E says, draw a diagram to represent the motion of the particle. So here's our diagram. Okay, this is how we draw these diagrams. These down here is going to be position. So the position 0. From what I found out right here, when t is less than 2, so at 0, I'll be moving forward all the way out to 2 seconds. At 2 seconds, I get a position, okay, right here. I'm plugging it into the position equation. Let's take it up top. At 2 seconds, I'll plug it into the position equation. I will plug it into the position equation, and I'll find out where I end up. Okay, so at 2 seconds, I will tell you right now, you will be at 32. So here's what we're going to do with that info. Let's move this up like this. I will have to figure out how I can move the rest of it up eventually. Okay, so now, over here, it's going to go forward, 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 forward. Right? This is t equals 0. And here, t equals 2. I'm at a position of 32. Right? Because I put it in s of t, and s of 2 came out to be 32. And then at t, I start moving backwards. Why? Because right here, I have negatives. So I start moving backwards in this direction. That's the position. That's the motion. Until I get to t equals 6. The position at t equals 6 is 0. So, right? So s of 6 actually comes out to be 0 when you plug it in. So that means I went all the way back to 0 right here. This is at t equals 6. And this is how we graph these. We graph the motion, write the time, but we're graphing position. And then it turns and goes back again in a positive direction and continues on. So this is the position graph, okay? Or the motion graph, I should say. All right, next we have to do part F, and part F says, find the distance traveled by the particle in the first 9 seconds. So to get the distance traveled, I need the positive direction and add it to the negative direction. Does that make sense? So in other words, I need to find certain intervals here. All right, so let's move all this up, and I can move these out of the way as well. And let's put letter F right here. And I need to know when it's forward and backwards. And I need to add these. All right, so backwards. I can spell that. All right, so right here, I have intervals from 0 to 2. It's moving forward. And then I have, and it says for the first 9 seconds. So let's look at the problem again. Notice in the problem, it said the first 9 seconds. So I'm only going out to 9. So then from 6 to 9, I'm also moving in that forward direction. Okay, backwards, I'm only moving backwards from 2 to 6. Now, it doesn't matter if you close these or open these on the intervals right now. All right, so over here, let's take a look at what we got. We are moving forwards from 0 to 2. So I need the distance, so I need the absolute value of s of 2 minus s of 0. Right? These should always all be absolute values, even though I know I'm moving forward. I work this out, I get 32 minus 0 in the absolute value, which gives me 32. All right, then I need s, this is another forward. Actually, this is backwards. Let's do the s of 6 minus s of 2. And when I do the absolute value here, it gives me 0 minus 32, and that's a distance of 32. And then I'm going to do the final one, which is s of 9 minus s of 6, and that'll give me 81 minus 0, which will yield 81. So I've traveled 32 forward, 32 backwards, and 81 again forward. I add this up, and I get a total distance traveled of 145 meters. So that's my total distance traveled right there. All right, so now let's move on to part G. Let's read what part G says. Part G says, find the acceleration after 6 seconds. All right, so let's move all this up again. We got to do all these things, all these pieces, because that's the way this does it. I guess I can group them together and worry about that later, but that's what I'm going to do right now. So for part G, we need to know the acceleration, which will be the derivative of the velocity, and that comes out to be, remember what my velocity equation is, I don't want to have to scroll back, so that comes out to be 6t minus the 24. I'll scroll back up for you guys so you can see it. The velocity equation right here was, we came up with 3t squared minus 24t, right? So velocity was 3t squared minus 24t, and we had plus 36, but then that constant goes away when I take the derivative. I need v prime of 6, which is a of 6 in this problem, and I will get negative 12 Let's rewrite that so it looks nice. Negative 12 meters per second squared. All right, so we can now move on to part H. Let me move again. All this stuff up, out of the way, forward, backward, all these things. And part H says we have to graph the position, velocity, and acceleration from 0 to 10. So I'm going to go ahead and put this on a grid for you, and I'm just going to go ahead and kind of look at the three equations that we have, right? And I will use different colors for these. We'll start with the S of t, and the S of t, for that position equation, we had t cubed minus, it was 12t squared, plus the 36t. And then we took the velocity equation, which was the derivative, 3t squared minus 24t plus 36, that's a t. And then let's do another color here, a different color. We'll do that. And this was our acceleration equation. And this was 6t minus 24. I'm going to graph each of these for you guys. It doesn't matter how you graph them. You can do it how you want. First, start with the position. I do want to put a couple key points here that we need. And then this graph went up and came back down like this. Okay. And then we had our velocity. And our velocity came probably through 4 right here, and I'm not worried about how high up and down on the graph. I just want to kind of show you guys something. And the velocity came down, reached that minimum, and back up this way. Oops, it went through 0 right here. Let's fix that. It went through the 2, came back, and went through the 6. All right, so then let's go ahead and graph the acceleration. And the acceleration function went through the 4 right there. Okay, went right through there. Let me fix the arrowhead there. Okay, but it only goes out to 10. I know I'm putting arrowheads, but we know that it goes out to 10. All right, I want to zoom in right now a little bit so I can write a few things. So let me talk about part I, what we're going to do. But I'm going to zoom in and move this all right up here so we can see. All right, so in part I, they want to know when it's speeding up and slowing down. So let's first examine some things. From 0 to 2, I know I'm moving forward. So let's put these values in here that we know. So from 0 to 2, we're moving forward, right? From 0 to 2. From 2 to 6, we're moving backwards. And then from 6 to 10, we're moving forward again. Okay, how do we know when something speeds up and slows down? So think of it this way. I can be walking in a forward direction and going faster. So my velocity is positive and my acceleration, let's write equals positive, and my acceleration is also positive. So that means I'm speeding up, right? But what if I was walking really fast with a forward velocity, but I'm being held back? So my acceleration is a negative value, okay? So something's holding me back. So obviously in this direction we could tell if that's happening, then I'm slowing down, okay? That's pretty obvious. Now, suppose, though, I was moving in a backwards direction. I'm going backwards. So that would mean my velocity would be negative. Now, if I'm going backwards, but my acceleration is in a positive manner, I'm also slowing down. Because I am moving backwards, but I'm being held back as I move backwards, so I'm slowing down. Or because the force is acting on me in a different direction. Whereas if I was moving backwards, my velocity would be negative,
and I'm being pushed backwards, I'm being forced backwards even more, now I'm speeding up. So here's what you need to know. If A of t and v of t are the same sign, then you are speeding up. If a of t and v of t are opposite signs, in other words, one is positive, the other is negative, then you are slowing down. Okay, so here are the two that we need to make sure we understand and memorize. So in part I, they ask for when are we speeding up or slowing down, and let's see if I can move this up here and answer that question. We are speeding up when we line up the v of t and the a of t to see which direction we're going. So let's first start with the v of t. And I'm going to put these on a number line, and this is how I like to do this. This is v of t. And I know that 2 and 6 I have found here. This was moving forward, this was moving backwards, and this was moving forward. So velocity was positive when I was greater than 6 and when I was less than 2, which means 0 to 2. And in between 2 and 6, my velocity was negative. Now I'm going to compare this to my a of t graph. So let's put that right below it, like this. And I'm going to say a of t, again, on a number line. And we came up with an a of t equation of, I believe it was 6t minus 24. Okay, if I take the 6 out, I'm left with t minus 4. So I know at t equals 4 right here. And we can compare that to the graph if we wanted to, this graph right here that we did, where we have, notice it's 2, 4, and 6 and the different lines. But I like to do it on a number line. I think that method is just a little bit more convenient. So I'll make this a little smaller so we could see what we did over here on the side. And when t was greater than 4, and I'm going to plug it into the equation right here. So suppose I had 10. Well, this would give me positive acceleration right in here. Okay, and when t was less than 4, say I had 0, I had negative acceleration in here. So here's what I want to do. I'm going to compare these, oops, I missed, these regions right there, and determine if I have the same sign or opposite signs. So right here, I look at this region, opposite sign, slowing down. Right here, same region, speeding up. Opposite sign, slowing down, same region, speeding up. So let's write these. So I'm speeding up, and I will use a different color right here to indicate that. I am speeding up where it was the same sign, so that's 2 less than t less than 4, which is between 2 and 4, and when t was greater than 6. I am slowing down when they are opposite signs, and that was between when t is less than 2, and then opposite signs when t was between 4 and 6. You can also write this in interval notation. You could say between, and now I just said less than 2. I probably should have said between 0 and 2 because we only go down to 0. But again, we are not going to be concerned with that since we don't consider a time less than 0. We don't have negative time. Well, I mean, I'm sure we're getting to the technology where we can find negative time, but as of this day and age, we don't have that, so we're not going to worry about that too much. But if you wanted to write it in this notation, you would write between 0 and 2, right? And technically, we should use open. It actually doesn't matter. It actually doesn't matter on the AP test. Um, it, it's one of those gray areas. You're neither speeding up nor slowing down, but we're not going to worry about that too much. And then between 4 and 6, like that. Over here, you could do the notation between 2 and 4, and we'll keep the open bracket notation. And here we'll say 6 to infinity, because we weren't specifically told where to stop in this problem. Actually, we could say till 9 if we were going from the original. But anyway, those are all parts of this problem. It's a very in-depth problem, but we learned when something speeds up and slows down. All right, so now let's go on to the next thing that we're going to talk about, and it's rectilinear motion. Here we use the derivative to describe the motion of a particle in a straight line. This is what we've been doing, and it's a very important, this should say theme, in calculus to study motion. Many books refer to a position as S of t, I've told you that. They'll say sometimes F of t or X of t. All right, here's another example. Similar to our last example, suppose S of t is this. What is the average velocity from 1 to 3? Okay, well, how do I find average velocity? Average velocity is not too bad. That means you want the average distance over the time. So that means I need S of 3 minus S of 1 all over this 3 minus 1. All right, and that'll give me the average. So over here, S of 3 would give me 3 squared, 9, plus 6, so that's 15, minus 3 is 12, over the 2, which give me 6, and this is units per second. Okay, that's my average velocity. This is an average. An instantaneous, I would need the derivative and plug in the point I'm looking for at that point. Okay, let's take a look at the next example. It says, a particle is moving along a horizontal line according to that. Determine the intervals where it's moving to the right and it's moving to the left. And I'm going to have us add something onto this. I want us to know when it's speeding up and when it's slowing down. Okay, so let's take a look over here. Again, excuse my writing because, like I said, my Apple Pencil for some reason is not working all of a sudden, so I'm using a stylus, and it's a big change for me. All right, so speeding up and slowing down is the thing we are adding to this. But before we do that, let's take a look at what we have. Over here, we need to know when it's moving to the left and to the right. So we need the velocity. So S prime of t will give me my velocity. And in this case, it's going to be 6t. I'll take the derivative, minus 3t squared. I want to know when it's 0, when it's stationary, so I could determine when it's moving to the right, which is a positive velocity, and when it's moving to the left, which is a negative velocity. So I want to know, first of all, when is it going to be stationary? When is it not going to move? So when is the velocity 0? So set it equal to 0 and solve this. Okay, over here, I'm going to take out a t and a 3, and I'll be left with 2 minus t, and we've got an answer of t equals 0 and t equals 2. So I'm going to put these on a number line, and I'll put it over here, and I'm going to label this v of t. Okay, I have 0 right here, and I'm not going to consider time less than 0, and I have 2. All right, so something between 0 and 2, I plug it into my velocity equation. You guys always ask me, where do I plug it into? Well, this is v of t, so you're plugging it into the velocity equation. Let's plug 1 in. You can plug it into this version or to this version. It doesn't matter. If I plug 1 in, I'll get a positive and a positive, so that means the interval between 0 and 2 will be positive. If I plug a number greater than 2, such as 3, 4, 5, I will get negatives when I plug it into v of t. Okay, and I'm not concerned with less than 0. Now I want to find the acceleration equation. So a of t, okay, so this is when I'm moving forward and I'm moving to the right and moving to the left. So let's finish this problem out before we continue on to the next one. So I'm moving forward, which is to the right, when t is between 0 and 2. I'm moving to the left, which is backwards, when t is greater than 2, so we'll say 2 to infinity, like that. Again, you can write it in the other notation, 0 less than t less than 2. You can also write it as t greater than 2. All right, so now let's take a look at when we're moving, when we're speeding up and when we're slowing down. So that means I need my acceleration. I started to do it here, and I take the derivative of the velocity. So this is going to be 6 minus 6t, and I set it equal to 0 because I want to know where there is no acceleration, first of all. So this will happen at t equals, so 6 minus 6t, and you can take a look at this and tell me that it's going to be at t equals 1. So now on a number line, I'm going to compare these two graphs, a of t, and here is 1. And anything when I put into the velocity, or to the acceleration equation, less than 1, such as 0, I will get a positive value, or 0.5 if you want to keep it that way. You don't want to use 0. And if I put something greater than it, such as 2, I will get negatives. So now we got to compare where we have the same sign and where we have different signs. So right here is one of the borders that I'm going to look at. Right here at 0, and then right here at 2. So I am speeding up when the signs are the same. So speeding up, okay, let's take a look. All right, between 0 and 1, I've got a velocity that's positive and acceleration that's positive. There you go. And then greater than 2, I've got a velocity that's negative, acceleration that's negative. I'm looking for the same sign for speeding up. So that's between 0 and 1, and in this case, it'll be 2 to infinity. Slowing down will occur between 1 and 2, and those are the only regions because where I have opposite signs. So this will be 1 to 2, and this is speeding up, slowing down. This was moving left and right, which is really forward and backwards. Okay, let's take a look at the next one over here. Rates of change examples. In an electric current, Ohm's law states that IR equals E, where E is the electromotive force in volts. I is the current amperes, and R is the resistance in ohms. Assuming that E is greater than 0, show that I decreases at a rate proportional to the inverse square of I. What is the instantaneous rate of change of I with respect to R in the electric circuit of 90 volts when R is 15? All right, so let's take a look at what we have here. For part A, we just have to show that I decreases at a rate proportional. Okay, well, as the inverse square of R. All right, so what I'm going to do here is, first of all, for part A, let's get a color on here. For part A, I'm going to go ahead and solve for that I. I'll get I equals E over R. Okay, well, now that I equals E over R, what I can do is take a derivative, because it's asking me for a rate. Whenever I take a rate, I want a derivative. So that means I need I prime, which is di over my dr. Okay? And in this case, because I'm doing it with respect to r, because they said inverse square of r. So I want to try to find something that relates r to it. And E is a constant. Okay, E is going to be our constant. And they even told us that it's greater than 0. So I take this derivative, and I will get negative, right here, okay, I will get negative E r to the negative 2. All right, so you could do it as E is a constant, change this to E r to the negative 1, and then take that derivative. That's what I did there. And now notice I've got a rate, and I can just clean this up and write it like this. I've got a rate proportional to the inverse square right there. Okay, so thus it decreases at a rate, because it's a negative, proportional to the inverse of the square. So I just showed that all in that part. Okay, part B. It says, what is the instantaneous rate of change of I with respect to R in an electric current 90 volts when R is 15? Well, I already solved this. I did the dI over dr. I found that in part A. And this was negative E over R squared. And they told me R is 15 and an electric current of 90. So 15 squared, and this will be negative and then 90. And that will result in negative 4.4. This is a 0.4. And that's going to be amps per ohm, are the units that we will be using there. There's many other examples that we can talk about here. We have business. I will do these in class, and a revenue structure. I will talk about these in class, but if you want to see them here, you can. And that one right there, and it's called marginal cost and marginal demand. Over here, you can break some of these variables up. You could say C of X is a total cost, average cost. Marginal is when we take a derivative. And then you can find an average. And again, I will do these examples in class. Moving on to the last page here. Let's go ahead and do these examples though. It says, the diagram shows V equals f of t of a particle moving in a straight line. When is it moving forward? When is it moving backwards? When is it speeding up? When is it slowing down? When is the acceleration positive? When is the acceleration negative? When does it move at the greatest speed? And when does it stand still for more than an instant? All right, so let's talk about this. First of all, for part A, let's see what we can do. For part A over here, we're asked to find when is it moving forward? When is it moving backwards? Okay, so forward is when the velocity is greater than 0, right? And we have a velocity function here. And so this is to the right. You can also think of it. Forward means to the right, and backwards means to the left. So if I'm looking at velocity, I want the velocity to be above the axis. That's when it's greater than 0. I'm looking at a graph of a velocity. I want the velocity to be above the axis. So this happens between 0 and 1, right here. From here to here, we have a positive. Okay, so you could put this on, if it even makes you want to see this on a number line graph, you can certainly make this into a number line graph, like this, right? And put right here, positive, from here to here, these are negatives. From here to here, this is positive. And then we've got 0, because it doesn't do anything. All right, so forward, we said, is going to be between 0 and 1. Okay, and then backwards, we said when it's going to be negative, that'll be between 1 and right here, which was at 1, 2, 3, 4, 5. And that'll be between 1 and 5. Okay, so then when is it speeding up and slowing down? First of all, we would need to find an acceleration. So we could do that for part B, and I'm going to put my acceleration graph right underneath this. This is at 1, and we said this was at 1, 2, 3, 4, 5. Okay, and this is 6, 7, and that's at 7 right there, just to help me out. Okay, and then I'm going to put my acceleration graph right directly underneath. And how am I going to find these accelerations? That's the million-dollar question. Well, look, you can look at the slopes, right? This is your acceleration. This over here was our velocity. And the million-dollar question was, how do I get the acceleration? Well, I'm looking at slopes because it's a derivative of velocity. So over here, I'm looking at this region up to 1 where I have a, actually, let's fix that, up to 2 where I have a negative slope. So that is a negative acceleration, right? So that's going to give me a negative acceleration. Then from 2 to 5, or actually from 2 to 3, I have 0. It's flat. It's not positive nor negative. It's a horizontal tangent. And then from 3 to, there's 1, 2, 3, 4, 5, 6, 3 to 6, I've got a positive slope. So that's a positive acceleration. And then from 6 to 7, we go negative again, and then from 7 on, we're at 0. Okay, it's neither positive nor negative. So that's what we got going on here. And now we have to check out the regions. Okay, the first region, second region, third region, fourth region, fifth region, and then the 7, that goes from 7 to 7. Okay, so I broke that up into regions. Kind of messy. I probably should have done it a little bit bigger. Maybe we can enlarge it and it won't look as messy. Maybe it will look just as messy. All right, let's write down when it's speeding up and slowing down. So speeding up. I am looking for the acceleration and the velocity to have the same sign. So we said between 0 and 1, I was above the axis, so it's positive. Let's put in some negatives here so we could see these also. These are all negatives inside of here, right? These are all negatives, okay? And then I've got my positive right here and then 0. So this was positive and positive right in here. All right, so let's take a look. Over here, these are opposites from 0 to 1. So let's also write our slowing down. So I can kind of do this all in one. Slowing down. Okay, so from 0 to 1, I know I'm slowing down. All right, so then let's take a look at the next little mini region here. From 1 to 2, from 1 to 2, my signs are the same, so I'm speeding up. So from 1 to 2, I'm speeding up. Okay, you can put unions or you can put ands. It doesn't matter either way. And now let's look at the next one. Okay, so I did 1 to 2. How about this? They're both 0, so it's standing still, neither speeding up nor slowing down. Then we get into this region. I've got a negative and a positive. So from 3 right here, let me clarify that. Okay, let's go back and clarify that. Here was that first region, right? I'm looking at this line. Here was the second region from, I said from 1 to 2. They were both the same sign. I had a negative slope and I was below the axis. Okay, then here's the next region from 2 to 3. Okay, from 2 to 3 I had a 0 here and I also was below the axis. Negative and 0 means, okay, nothing's happening in acceleration, so I'm neither speeding up nor slowing down. Okay, then, because it's not opposite signs or the same sign. Then I'm looking at the region here between 3 and 5. Okay, so between 3 and 5, I'm looking at this region. That's why I broke these up into different little mini regions here. From 3 to 5, I have a negative velocity, okay, because I'm below the axis, but I have a positive acceleration because it's a positive slope. So these are opposites, which means it's slowing down from 3 to 5. So slowing down, I would add that in from 3 to 5. All right, let's see what next region I have. Over here, from 5 to 6, I've got a positive, it's above the axis, and I've got a positive slope. So that means it's speeding up from 5 to 6. All right, let's see what else I got. Okay, next, from 6 to 7, I am above the axis, positive, but I am negative slope. That's negative. Opposite signs, I'm slowing down. So let's add that in. That would be 6 to 7. Union 6 to 7. I am slowing down as well. So those are all the spots where I'm speeding up and slowing down. Okay. If it wasn't included in that, then it's neither. You're neither speeding up nor you're slowing down. For part D, when is the acceleration positive? We had already said that between 3 and 7. That's when I was when I had a positive slope between 3, right here, and 4, 5, 6. Sorry, between 3 and 6, I had a positive slope. So that would be the acceleration is positive between 3 and 6. Negative acceleration, when I had a negative slope, that was between 0 to 2. And I had another one over here, which was between 6 and 7. All right, and now for part C, it says, when is it moving the greatest speed? Well, the greatest speed is when the velocity, the absolute value, I should say not average, but the absolute value of the velocity has to be the greatest. That's when it's having the greatest speed. So I have to take a look at this one, and I got to take a look at this one. Okay, this is, I didn't put a grid on here, but these are probably, I think I had made these in twos, and this would be a -1 and this would be 2. So this would be at t equals 0. I should have clarified that on the grid there, but I didn't do that so well. And when does it stand still for more than an instant? Well, standing still for more than an instant, that means the velocity is not moving and there's no acceleration. So the only spot where we've got the velocity not moving and no acceleration is right here, and that's going to be between 7 and 9. Okay, we don't know what goes on past that because the graph ends right there. One thing I just noticed too here, moving forward, I said between, I just noticed when I was looking at the graph, I said between 0 and 1, we are moving forward because the velocity is above the axis. I forgot to add in also, look right here, above the axis between, that'd be 5 and 7. 5 less than t less than 7. So those are the spots where it is moving forward. All right, if you're looking at this, it looks like a nightmare, and I'm sorry. I apologize putting it all in, trying to do it underneath and not enough space, but hopefully you understand what was happening here. So I'm going to do one more problem for you, so let's take a look at this. I'm not going to do the last one, we will do that in class, but let's take a look at this next one right here. It says the graph of s of t, a particle p, is shown. When is it moving to the right and to the left? So remember though, the key that they just told us right now, this is an s of t graph. Okay, it is not a v of t. This is a position graph. When is it moving to the right? Well, when is it moving to the right is when the velocity, right, is going to be positive. The velocity is going to be positive, is going to be to the right, right? So v of t has to be greater than 0, and we're moving to the right. V of t less than 0, and we're moving to the left. All right, so let's find out what these spots are. How do I find that? Well, since I'm looking at a position, I need to find the slopes. So over here, the slope is positive between 0 and 1, so that means it's moving to the right. So that would be between 0 and 1. Let's take a look at the next slope. The next slope is horizontal. That's not right or left. It's standing still. So let's add that in. Standing still. So that would mean the velocity is 0. And that happens when I have the horizontal tangent. That's between 1 and 2. Okay, so then let's take a look at the next thing here. From 2 to 3, it's negative, so that means it's moving to the left. So that's 2 to 3. Okay, then from the next part, from 3 to 3, 4, 5, again, it's standing still. So that's from 3 to 5. So we'll put a union from 3 to 5. Okay, next, we got negative from 6. From 5 to 6 is going to be a negative slope, so we'll put, that's moving to the left. So this is going to be between 5 and 6. Okay, for part B, graph the velocity and the speed. Okay, so when I'm graphing velocity and speed on these, let me explain something to you guys. Remember, velocity, I'm doing what actually is happening, and I'm going to put it right underneath here, v of t. And then the other one I'll do right underneath here as well, and I'm going to do speed. Okay, and remember, speed is going to be the absolute value of the velocity. So for the velocity part, okay, between 0 and 1, remember, what is velocity? Velocity, for part B, okay, for part B, get back to the pen, there you go. For part B, velocity is delta S over delta T, right? So my change in position over my change in time, right here, I went from 0 to 1, I've got a slope of 2. So 1, 2. right here, and that will be from here, open circle, to here, open circle. This is at 1. Okay, and then at 2, I've got, it's flat, it's not moving any, so that's open circle, shaded in between. All right, and then from 3, I'm sorry, from 2 to 3, from 2 to 3, 1, 2, 3, right there, I'm down at a slope of, I went down 2, 4 over 1, so I'm at negative 4. 1, 2, 3, negative 4. I'm right here. I'm graphing the slopes, right? The velocity means I'm going to graph the slopes of these, of s of t. And then we're back to 0 all the way out to, that would be from 3, 4, 5. 3, 4, 5. I'm back to 0. Shade in between, open circles. Okay? And then I've got, again, this slope now is negative 2. So from here to there, I'm at negative 2. Well, the speed is going to be similar. The only difference is I don't have any of those negative values. So let's do that in a red color. So over here, I'll go up to 1, 2, open circle, like this. I'll have a 0 right there. And then the next one, I'll go up to 4. 1, 2, 3, 4. And I'll put that there, because I won't have any negatives. Then I'm back down to 0 to here. And then this, again, goes up to a positive 2. So speed, I'm just taking and getting rid of any of these negative ones down here. All right, I will do the last one when we meet together in class. So thanks for watching. Hit that like and subscribe button, and I will see you guys in the next video.